Hello and welcome everybody to Midas Civil Advanced Webinar Series. The topic of today's advanced webinar is pre-stressed concrete with FCM bridge. And throughout the course of the webinar, I will introduce before you the pre-stressed concrete modeling and analysis and design in front of you. Then I'll move on to the modeling features, covering the bridge wizards. I will talk about the analysis control. And finally, I'll talk about the results and the design check for the pre-stressed concrete bridges as per Midas Civil. Throughout the course of my webinar, I would also model an FCM bridge in front of you by element modeling, and I'll show you how the different tendons or reinforcement or tapered section groups are defined in Midas Civil and how easy is it to model those sections. So let's start with the advanced webinar. Midas Civil contains a database of a variety of pre-stressed sections that can be used directly by the users for the modeling of the pre-stressed bridges. If you go to the properties, section properties, under the PSC tab, the users will see that a wide variety of sections are available from which the users can choose the sections for the modeling of their bridges. Also, apart from the PSC 1 cell, 2 cell and n cell sections, the users can also select the sections defined in ASTO codes such as ASTO type 1 to type 6, the Caltrans code such as Caltrans sections 3, 3640, and apart from that, the users can also select the sections from the database of UK and Italy codes. Again, if the section doesn't match with the section that you're going to use for the construction of the bridge, then you can define the section by defining the section coordinates, or you can import the section defined in SPC. I'll talk about it later in detail. How is it done? How do we import the section from SPC? But before that, I would like to tell you something about this option known as mesh size for stiffness calculation. If you see here, in Midas Civil, the torsional moment of inertia and the effective shear area is calculated by this methodology. What Midas Civil does, when the user defines a section, Midas Civil creates a meshed element of length 20 meters and applies a unit load at the centroid of the section, and the element is a cantilever beam. And with the help of torsional rotation, Midas Civil that calculates the torsional moment of inertia and the effective shear area. If the user feels that the moment of inertia, the torsional moment of inertia or the effective shear area is not as what he expected, then the user can select his own mesh size and he can obtain the desired torsional moment of inertia. Also, the tapered section for the PSC can be defined under the taper tab. In the taper tab, you will see a variety of options such as the PSC 1 cell the PSC 2 cell and the PSC n cell. Here you can import two different sections which you have previously defined. As you can see here, you can import the size I as well as you can import the size J, which you have already defined under the PSC tab. Also, you can define the tapered section for the PSC value type. The PSC value type implies the sections that are generated in the section property calculator. So let's talk about the section property calculator now. If you go to tools, you will see an option, section property calculator. Section property calculator is a very versatile module of Midas Civil which allows the users to create sections either by using the inbuilt geometry of section property calculator, such as you can create curves, polylines, or you can create rectangles, circles, ellipse, and cubic curves, etc. Or you can import the section that you have previously modeled in an AutoCAD drawing sheet. Now I will demonstrate before you how you can import the section from the AutoCAD file and how can you export that section to be used in Midas Civil for analysis and design. If I go to the file import, I can import either an SPC previously made project or I can import the AutoCAD DXF file. So this is the section that I previously generated in my AutoCAD sheet, and now I'm going to create a PHP section out of this type of section. So I'll go to Model, Section, Generate Section. Here you can select either a plain type section or a line type section. Since PSC is not a line type section, but it is a plain type section, so I'll select the plain type section and I'll give it a name. And I will select all the lines of the section and I'll select the option Calculate Properties now and I'll click on Apply. And as you can see here, Midas Civil first created a meshed section for the calculation of properties, and the properties are then listed in the list section properties. Here as you can see, the various properties, the area, shear area in X and Y direction, the moment of inertias, and so on and so forth. Also, talking about SPC, you can also model the composite sections in SPC. You can model the sections up to 4 parts in SPC. Now we are ready to export this section to Midas Civil. So I go to Model, Section, Export. I'll select the Midas section file and I'll give it a name. Let's say 4-cell section. And I select the section and I click on Apply to export the section. Now I'm ready to import the section in Midas Civil. Here the important thing to remember is that if you are trying to import a PSC section that you would use for the design also, then you must import it under the PSC tab. If you import it under the Value tab, then Midas Civil will not do the design check for the section. So I went to the PSC tab and I selected the PSC value type and I import the section from SPC. So as you can see here, I have imported the section that I defined in PSC in SPC, and now I'll define certain parameters for shear check, and I will define the thickness for torsion and certain other parameters as defined for the design check. I'll give it a section name. And I will generate a beam to demonstrate how the section looks like. So as you can see here, I first imported the line diagram from AutoCAD drawing to SPC, then I created a section out of it in SPC and imported the section in Midas Civil, and I have generated an element with that section. So this is how the SPC can be used for the modeling of different sections. Now I would like to tell you about a peculiar characteristic that users must know and must understand for SPC. As you can see here, I modeled two different sections in SPC, and I would like to use them as a tapered section for my modeling in Midas Civil. So the users must understand that the units must be consistent with the AutoCAD file units. So if you have done the drawing in AutoCAD using meter as the units, then you should select the SPC units as meters before importing the section. And the second thing to be kept in mind is that while you define the tapered sections, the number of points must be same. So as you can see here, both the sections are exactly similar except the depth, and there is an additional point here on the top section. So if you try to make a tapered section out of it in Midas Civil will show an error. Now going back to my original idea of modeling a pre-stressed balanced cantilever bridge or the FCM bridge in front of you, I will open a model in which I have done the geometry. So this is how the model looks like. The section is a 2-cell section, but if you'll notice here, the depth of the section is constant all through, and this is not what is desired. I want to vary the depth from this end to this end, and the depth increases as I move towards a support. So now I will try to model the bridge in such a manner that the depth of the section increases from an end support to the mid support, and then it decreases towards the mid span and again increases towards the second support and decreases towards the mid span again. For that, I will use a special bridge wizard feature of Midas Civil known as PSA Bridge Wizard. Here you can define the spans, and then after defining the spans you can define the reinforcement by span, and you can vary the depth of the span as per requirement. So first I will define the span. I name it as span number 1, and I define the supports for the span. Here the user must understand that these supports are just the nomenclature. That is, these supports bear no correspondence with reality. They are just the nomenclature to be used for defining the reinforcements or defining the section depth, etc. Similarly, I'll define span number 2. And again, I'll define the supports. And similarly, I'll define span number 3. So I have defined the 3 spans, and the span information appears in the works tree. And if you double click on a span, you can see the span definition. Now I'm ready to make the tapered section with the help of the PSA Bridge Wizard. So I will go to the PSA Bridge Wizard. I will go to the section and reinforcement, and I'll select the span 1. I'll select the typical section, and now I will define the section depth. So at the eye end, I want the section depth to be 2 meters, and on the second support I want it to be equal to 4 meters. So as you can see here, I can select the curve type as the straight line or the curved line, and if I select the curved line, I can define the exponent also. So the exponent is the degree of the polynomial that you want to use for the depth variation along the length of the bridge. Similarly, I will do this for the other spans. Now I would like to define the section depth for the span 2. But here I would like to tell you that we need to be very careful. Why we need to be careful? I'll let you know now. Here, if the curve type is a curved line, then the symmetrical plane must be wisely selected, otherwise the profile may not be what is desired. I'll let you know what does it mean by this. So here, as you can see, I used the PSC bridge structure wizard for defining the depth of the section variation from 2 meters at this point to 4 meters at this point, and I selected the symmetrical plane distance as 0 meters. So it implies that the symmetric plane is here and the curve will be made like this. But on the other hand, if we see this image, the span is on the right side of the support, which implies that support I is here and support J is here. And I have selected the symmetrical plane to be at 0 distance. So the symmetrical plane will be here, and you can see how the depth varies with this. And hence the symmetrical plane must be wisely selected so that I can get the required profile of the bridge. So while I'll define the section depth for span 2, I will select the symmetrical plane to be at a distance of 25 meters from the support. And now I have defined how the section width depth varies with the length of the bridge. So the depth will be 4 meters here, and it will decrease to 2 meter at the center of the span and again increase to 4 meter at the other support. Now I'll define similarly the depth of the section variation in the third span. And since the span is on the right hand side, I'll have to define the symmetrical plane again. The symmetrical plane is on the user's choice, so I chose it to be at the distance of 25 meters for convenience. Here I varied the height of the section, and you can also vary the width, the top flange thickness, the bottom flange thickness, the external web thickness, and the internal web thickness also. So it's a very versatile tool that can be used for the variation of not only the height, but the width, top flange thickness, bottom flange thickness, and etc. So I have defined how the thickness varies along with different spans. And if I go to the reinforcement tab now, I can define the reinforcement as desired. We can define the reinforcement either by defining section by section reinforcement, or we can define the reinforcement by the span. So let's say I want to define certain reinforcement for span number 1, and from support 1, that is at the leftmost end of the bridge, this point to half of the span, I want to specify certain reinforcement. And as you can see here, I have defined the reinforcement to be the start point at support 1 and the end point at the 0.5 times of span 1. So I'll define certain diameters. So as you can see here in the display, you can see the reinforcements also. And you can vary the spacing if the spacing is not as you desired. And if in by chance you inputted a wrong spacing, then it goes out of the section and the user can see that it's improper. So this is the top reinforcement that I have defined, and now I'll define the bottom reinforcement. So I'll select the reference from bottom and I'll use the same clearance. And as you can see, I have defined the bottom reinforcement from support 1 to mid span, and I'll click on add. Now I'll define the reinforcement from 0.5 times of span 1 to the support 2. Here the user can also define the distance. That is, let's say the span length is 100 meters and I from first 100 meter from 0 meters to 10 meters I want this much of reinforcement, from 10 meters to 80 meters I want this much of reinforcement, and etc. So here I will increase the number of reinforcements and I'll decrease the spacing, and the bottom reinforcement remains the same. So as you can see here, I have defined the reinforcement for span. I can also define the shear reinforcement and the torsional reinforcement as desired. Once I click OK, the program will take some time to generate the tapered sections, and you can see here right now the number of sections are 2, and once this thing is completed, the number of sections will increase and all the tapered sections will appear as desired. Again, I would like to highlight that we need to be very careful while we define the symmetric plane, because it is needed for the generation of the tapered section along the length of the bridge. So as you can see here, Midas Civil has automatically calculated the depth as required by the user. The depth of the section at this end is 2 meters and at the support is 4 meters, and it varies as desired by the user. So this is what it means, and on the left hand side you can see the number of sections has increased to 42. So Midas Civil has automatically calculated what section depth is required, and also the reinforcements have been updated to different sections. So as you can see, if you click on the reinforcement bars, you can see the reinforcement bars in the section. And you can also take the rebar data from here, which gives the tabular input of the rebar data. So this was about the tapered section and the definition of the reinforcement. The third thing that the PSC Bridge Wizard does is the definition of effective width. The user can define the automatic effective width as per the ASTO LRFT code. And when I selected the ASTO LRFT code, the effective width has been computed as per the ASTO LRFT. And in the message window, as you can see, the effective width has been calculated. Also, if you don't want the automatic effective width of ASTO LRFT, then you can define your own effective width scale factor. As you can see here, if you go to model, boundaries, effective width scale factor, you can define effective width for IY, and you can also vary the scale factor for the Z from the top and Z from the bottom for the determination of section modulus. The other thing that is to be noted here is that the effective width scale factor is only used for the calculation of sectional stresses, and for the global analysis, that is the determination of stiffness matrix, it is not used. But if you define a section stiffness scale factor, which you can define under the section manager, if I select a section, let's say, I can define the section stiffness scale factor here, and this scale factor is applied to both the calculation of stresses as well as the determination of stiffness matrix. So the user must understand the difference between the effective width scale factor and the section stiffness scale factor, as I told just now. Now moving on to our modeling, I will model in front of you the tendons now. So let's say I want to model the tendons in these two elements. So I selected the elements and I will activate them. So this is the section where I want to define the tendons. So I define the tendon profile with the help of inbuilt tendon geometry definition dialog box, and I will select the elements on which I want to assign the tendon. And here I can select the input type as 2D and 3D, and I can select the typical tendon. The typical tendon, as the name implies, is assigned to a group of tendons. So let's say we have 10 tendons. With the help of this typical tendon, we can define only one tendon profile, and if we select the number of tendons in the typical tendon as 10, then the effect will be as 10 times the effect of one tendon. Now I will define the tendon definition. So as you can see here, I have defined a tendon which has a straight profile and which is at an offset of 0.2 meters from the top of the section. One thing that I would like to tell you here is that the user can select the reference axis to be straight, curved, or element, but there is some difference in these three options, and now I will tell you what is the difference. If you select the element type, you can define the tendon along the element, and if you select the straight or the curved type of reference axis, then you'll have to define the tendon in the global coordinates. So if you select the element reference axis, then let's say I have defined two tendons, one in yellow color and the other in red color, as per the element reference axis. If you check the tendon length in the tendon weight table, then you would realize that the length of the tendon yellow is lesser than what it will be in the actual field because of the disturbances here. Since the element, we have modeled a curved element with the help of different lines, so the length of this tendon will be lesser as what it will be in the field, and the length of the tendon in red will be greater than what it would be at the field. So this is one difference if you select the element type while defining the tendons to the curved elements. And the second is when you select the element option, the friction loss due to curvature is not considered. So let's say this is the profile of the element as seen from the plan, and the tendon has the exact same profile as the element. Then the curvature loss due to global curvature is not considered, but had we have a tendon like this, then the friction loss due to the curvature would be calculated. Now I will define another tendon in front of you to demonstrate before you the use of the x-axis rotation angle and the offsets. So I changed the unit system to be from Newton meter to Newton millimeter. And now I'm defining the tendon coordinates. So I've defined the tendon like this, and now I will define the x-axis rotation angle as per the angle of the web. So what am I trying to do is that I'm trying to define the tendon in the web which has certain degree of inclination with the x-axis. So I'll define the offset to the tendon. So as you can see here, I defined the tendon in the middle of the section, and I used the section offset to define the tendon profile. So as you can see here, I have defined the tendon in the web portion very easily by defining the rotation of the tendon as per the x-axis, and I defined certain offsets. So what I did, I defined the tendon here and I provided it an offset and rotation as per the x-axis. So this is how the tendon inbuilt geometry profile definition dialog box can be used. Now I will demonstrate before you how we can export the tendon to the AutoCAD file. For that, let's say I want to export this tendon to the AutoCAD file, then I can just select the tendon, click on export to DXF, and while clicking on export, the tendon will be exported. Also, the user can import the tendon from the existing AutoCAD file. This is how the user can do that. If the user goes to Tools and Tendon Profile Generator, the user can import the tendon So this is the tendon profile that I defined in my AutoCAD file, and I want to use it as the tendon in my model. I will assign it to certain number of elements. And I will select the tendon for the XZ and the XY plane. One thing that the user must understand here is that if we export a tendon from Midas Civil to the AutoCAD DXF file, then two tendon profiles are generated for the same tendon. One tendon profile is the tendon profile in the XZ plane, and the other tendon profile is the tendon profile in the XY plane. So once I click on add and click on OK, the tendon profile generator will give me the tendon coordinates at certain lengths. I copied the tendon coordinates and I pasted them into the MCT command shell, and once I click on run, the tendon profile is inputted. So as you can see here in the display, this is the tendon that I defined in AutoCAD file, and I imported that tendon to be used in Midas Civil. Now let's talk about the bridge wizards that are available in Midas Civil for the quick modeling of the bridges. So if I go to Model Structure Wizard, the user can select the bridge wizards that are available for pre-stressed concrete bridges. The user can select the ILM Bridge Model Wizard. Here the user has to define certain geometry of the ILM bridge and the tendons. Also, the user can model the boundaries. The user can define what are the temporary and the final boundaries, and accordingly, in the other ILM Bridge Model Stage Wizard, the user can select the reference axis for the ILM bridge motion. Since the ILM bridge is pushed from one end to the other end, the user can specify the direction from the start and the end node with the reference node in between, and the user can also model the stages as required. Also, the user can use the structure wizard for the FCM bridge. Here, not only the FCM bridge, straight FCM bridge, but the curved FCM bridge with a certain degree of radius can also be modeled. Also, the user can specify either the default section used in the library of Midas Civil, or it can define its own section for the generation of FCM bridge. The own section will be defined in the section properties in the PSC tab. Also, the MSS Bridge Wizard can be used for the modeling of MSS bridges. The cold joint can also be defined. Its distance from the support can be designed. Also, the FSM bridge, that is the full stage modeling construction method, the wizard is available for that too, and the user can quickly generate the tendon profiles and etc. for the modeling of this kind of bridge. If you select the type 2 section, the user can define its own section as required. So this was about the various bridge wizards that are available in Midas Civil for the modeling of the bridges, for the quick modeling of the bridges. But if your bridge doesn't fall in any one of these categories, then you can do the element by element modeling and specify certain parameters and analyze the bridge as required. Also, there are certain moving load codes that are already incorporated, and the user can select either one of them for the moving load analysis. So this was all about the modeling features. Now let's talk about the certain analysis features that the user can select from for the analysis of the pre-stressed concrete bridges. So the first is the tendon tension loss effect. If you go to Analysis, Construction Stage Analysis Control, under the time dependent effect control, you will see the option tendon tension loss effect for creep and shrinkage. If you check on this option, the tendon loss due to creep and shrinkage will appear. Also, the user can select whether the rebar confinement effect has to be taken into consideration or not. Finally, the user can select the initial tangent displacement for erected structures. I'll let you know what does that mean. So this is an FCM bridge that I'm going to construct in reality, and this is the new segment that I'm supposed to add. But since before this new segment can be added, I have certain degree of rotation at this node where this element has to be added. In Midas Civil, you can see that deflection due to that node, and you can do that by selecting the option Initial Tangent Displacement for Erected Structures. So this was about the analysis control that the user can select. The user can select the initial tangent displacement, or the user can select the beam section property. How does it change or remain constant with the tendon? If the user selects the beam section property to remain constant, the beam section properties remain constant throughout the analysis of the bridge. But if the user selects the beam section properties to change with tendon, all the parameters of the section changes along with the tendon. Also, the user can select the frame output results. It can calculate the concurrent forces of frame, and it can also calculate the output of each part of composite section if you have defined a composite section as such. So this was all about the modeling. Now I would like to open another model in front of you to show you the analysis results. So this is the FCM bridge that I modeled. I have defined certain moving loads, I have defined certain tendon profiles, and I have defined the stages also. So as I told you in the previous webinar about the construction stage analysis, first let me run the analysis here. So as I told you before, the construction stages in the FCM bridge can be modeled by defining certain groups. And how do we define groups? We go to the group tab in the works tree and we'll define certain groups. So as you can see here, I have defined the peer groups and the different segment groups. And when the segments are constructed in actual practice, or the segments are activated, that means let's say we have the cast in situ FCM construction type of bridge, then we can model the dead load of the segment that has wet concrete still in our structure using the nodal loads, and when it adds to the stiffness of the structure, we can activate it. So first we need to define the groups, and accordingly we define the boundary groups for the same. The boundaries can be activated or deactivated as desired. Also, the load groups can be defined and activated as required. So as you can see here, I have defined certain stages. I have defined 16 stages, and if I go to individual stage, I can see what are the different elements that I have activated, what are the different boundaries that I have activated, and what are the different loads that I have activated or deactivated. So let's check out the construction stages of this FCM bridge. If I go to stage 1, it contains the pier and the pier table, and moving forth you can see how does the construction of this balanced cantilever, that is the FCM bridge, goes on. Now let's talk about the results. And the convention results such as the beam diagrams, the bending moment diagrams for different stages can be seen. For dead load, erection load or the tendon loads, etc. So let's say I'm interested in finding the bending moment for the dead load in different stages. So this is the bending moment diagram and how does it vary along with different stages. Also, I can see the PSC beam stresses for 10 different positions for 10 different components, and I can see that for various stages accordingly. Apart from the conventional beam diagrams, I can also see the stage step history graph. In the stage step history graph, you can specify a certain force effect such as the bending moment or the shear force, and then you can see how does it vary along with the time. So this is how I have defined the element number 24, and I want to see how does the moment at the I node changes along with time. So if I select on this and click on graph, this is how the bending moment due to dead load changes at the I end of the element number 24. If I go to the bridge girder diagrams, here I can see how does the bending moment varies along the certain predefined bridge girder element groups, and I can also draw the allowable stress line accordingly. So let's say I want to see the bridge girder diagrams. I want to see the stress, let's say, due to bending, and I want to draw the allowable stress line. Then Midas Civil automatically generates the stress and the allowable stress lines as shown. Apart from these results, Midas Civil also equips the user with FCM graph. So you can generate the FCM graph either in the graphical format, and if you see the details of the graphical format, you can see that for every node we have two values here. The two values are the cambers that need to be provided to the bridge before and after the scaffolding is removed. So the user must know the difference between the two values. And also the table for the FCM camber can be generated. So this is the camber that is to be provided to different nodes, and at the end construction stage the user will obtain a straight profile of the bridge. Also, the results related to tendon, such as the tendon loss table, can be generated. Let me tell you more about the tendon loss table. If you see the tendon loss table, you can see the stress after immediate loss is A, elastic deformation loss B. I'll let you know what does that mean. So the stress after immediate loss A for the post-tension beams, it includes the instantaneous loss such as the friction loss and the anchorage loss. And for the free tension beams, it includes the elastic shortening loss only due to pre-stressing and not due to self-weight or all other loads. So this is the anchorage loss equation that is used in Midas Civil, and this is the friction conventional equation used in Midas Civil for the determination of friction loss. The elastic deformation loss B, it contains the pre-stress losses due to the secondary loads such as the self-weight, live loads, and creep and shrinkage, etc. And it for the post-tension bridges, let's say we have two tendons that are pre-stressed at different time intervals. So when we pre-stress first tendon, there would be no elastic shortening loss because we consider that the jacking force will be automatically adjusted for that. But when you pre-stress second tendon, there would be some elastic shortening loss in the first tendon, and the elastic deformation loss P will tell you what is that loss. Again, you can see the creep and shrinkage losses and the relaxation losses. And when CBFIP is selected to be the code for the relaxation losses, then this is the equation that is used. So this was about the tendon losses. You can also see the tendon elongation. The tendon elongation implies what elongation has to be provided to the tendon so that the desired stress level can be obtained. Also, the tendon weight shows the tendon length and the area in a concise format. Also, the user can see the construction stage results such as the beam section properties at last stage. As you can see here, the users can see the area, the moment of inertias, and the centroid location, etc. here. And finally, the user can generate the tables for the beam, stresses, forces, etc. So that was all about the results associated with the pre-stressed concrete bridges in Midas Civil. Now let's talk about the design. In Midas Civil, you can perform the design using the ASTO LRFT code or the Euro code as desired. And after defining certain parameters for the material and the position, you are ready to design the bridge. So once you design the bridge, you can see the moment of resistance, the flexural moment of resistance, the shear moment of resistance, and you can see the combined shear and torsion and the various serviceability limit states such as the stresses in the tendons, the stresses in the reinforcement bars, the stresses in the concrete, and whether they are in the allowable range or not. So if you go to the PSC design result tables, you can check stresses for cross-section at construction stages. These are the various symbols that are used. FT determines the stress at the top, FP determines the stress at the bottom, and so on and so forth. Also, the user can see the flexural strength for the members, and the check implies whether it is under the safe limit or not. So the various parameters that are used in the code are used. Also, the user can do the calculations, the PSC design calculations, which implies that the Midas Civil will give you an output in an Excel format, and the user can see what are the different parameters that are used in Midas Civil for the same. So once we generate the Excel sheet, so as the Excel sheet has been generated and the user can see the parameters for the flexure design, the user can see the parameters for principal stresses, tendon stresses, crack check, torsion design, etc. in this Excel format. So this is a concise report format generated by Midas Civil. So this was about the analysis and design of pre-stressed concrete bridges as per Midas Civil. Thanks for being with me during the webinar, and I hope it equip you with the certain required essential knowledge for the modeling of the bridges. You can send me any queries at esupport@midasit.com, and I'll be more than happy to answer any queries any further. Thank you very much. Have a good day ahead.